so all of a sudden, the cabin in one part of the space station just became thick with a pall of smoke. And of course, all the air handlers then moved all that smoke around the spacecraft. So within about 2 hours, the entire spacecraft was completely filled with smoke. So we had to just wait for the air handlers to scrub all of this contamination out. And that took about 2 days. And we all manifested symptoms of the toxicity of that environment. When there's a lot of carbon monoxide at those levels, you have nausea, a certain amount of confusion, invariably a headache because you're oxygen deprived. It's just a very uncomfortable feeling.
The dangers of fire in space go beyond the fact that you can't open a window or call the fire department. Fire actually behaves differently inside a spacecraft in zero gravity.
What we are seeing is a candle flame. The bottom one is a candle in normal gravity. And as you can see, the flame moves up because buoyancy pushes the hot gases around the flame up. The top photograph is the same candle, but in the absence of gravity.
Columbia Space Park for the module. A mist burn will be initiated here in about 15 seconds.
The hot gases don't move up, and what you have is a spherical flame.
There's the flame. So here's the initial light off for combustion module 2.
So putting a smoke detector on the ceiling, like we do on Earth, doesn't work in space. Instead, detectors are located next to small suction devices that draw air and any smoke or other toxins toward the detector. To figure out just how dangerous fire is in space, Professor Fernandez-Peyo's team performs experiments in the University of California, Berkeley Combustion Lab and on KC-135 aircraft in short bursts of zero-G. In theory, fires in zero gravity should be less intense because the hot gases don't rise, which means cool air isn't drawn in at the base to keep feeding the flames. But they're finding that the reality inside a spacecraft is more dangerous. Air conditioning systems create small air currents. Those currents bring fresh air, or in this case, fuel, to the fire. At the same time, the low airflow and lack of gravity don't remove the heat as quickly as on Earth. The result?
This type of fires are hotter and more dangerous than in normal gravity.
And fire is likely to become even more of a safety hazard inside the new Ares Orion spacecraft being designed to replace the shuttle.
What they've decided to do was to reduce the pressure and increase the oxygen. And by doing this, they reduce the preparation time that it takes for the astronauts to go from the vehicle to outside of the vehicle. So what we're doing is we're testing materials at that proposed environment. We've learned that for the environment that they've chosen for the next generation of vehicles, things actually ignite about 20% faster than they would in the current environment.
The combination of high oxygen content and low airflow means just about anything can catch fire, even metal. In a worst-case future scenario, a space station crew is unable to quickly extinguish a fire. It grows too fast to seal off in a separate module. Even if they put on emergency oxygen masks, the heat of the flames will likely kill them. And if they're somehow able to survive the flames, the filtering system is completely overloaded. They are left to die in a toxic stew from smoke inhalation. The best chance of survival with an out-of-control fire is to abandon ship and return in a re-entry capsule if one is available. That was the key to the survival of the crew of Apollo 13. April 11th, 1970, the three-man crew launches into space. 2 days later, on their way to the moon, an oxygen tank suddenly explodes. The explosion causes a substantial loss of oxygen and damages the service module's electrical system. The crew is forced to live in the cramped lunar capsule.
Apollo 13 is the classic case of the failure that doesn't kill you. It happened at the right time. It happened when they were on their way to the moon, so they could use the lunar module as a lifeboat and get back to Earth. Had the same problem occurred after the lunar landing, when Lovell, Swigert, and Hayes were on their way back to Earth, there would have been nothing they could do. They would have been dead.
The threat of fire is especially high inside spacesuits. During spacewalks, also known as EVAs or extravehicular activity, the spacesuits need to be kept at low pressures. Working in a fraction of Earth's atmosphere is the key to flexibility.
If you had a spacesuit that was at 1 atmosphere, you would be like basically in a balloon, and you couldn't move.
With low pressure, just like a climber in the thin atmosphere of Mount Everest, astronauts need to breathe highly flammable 100% oxygen.
This is an arm from the spacesuit. It was burned up in a fire in 1980 at Johnson Space Center. Just doing some checkout tests, pressurizing the system with the 2 different oxygen sources. And when this fire occurred, it was, quite a shock. People were standing nearby it, and someone was supposed to be in the suit the next day for a manned test, and it could have been a fatal fire. Even as it is, this suit is worth, at the time, $3.1 million. And it also took NASA $20 million to recover from this fire in terms of redesigning the suit.
Extravehicular activity is dangerous for many other reasons as well. In fact, the world's first spacewalk almost ended in disaster.
Alexei Leonov did the first spacewalk that any human did in 1965. But in the rush to accomplish that space spectacular and thereby beat the Americans, the Soviets took some shortcuts on the safety of the cosmonaut. And so he blew up like the Michelin Man.
The suit became rigid. It couldn't handle the pressure differences between the breathable atmosphere inside and the vacuum of space.
The problem is you've got a spacecraft in the Soyuz capsule that he was flying that's very small, and the hatch for it is even smaller. Ultimately, his response was to let a little bit of the air out and just deflate the thing enough so that he could crawl back in through the hatch. But he will tell you that to this day, that he wasn't sure he'd be able to make it.
An astronaut having, like Leonov, to let the pressure out in order to be able to maneuver in it is in the same situation as a diver ascending from deep water too quickly. Nitrogen bubbles will form in your bloodstream and not only be painful, they'll kill you.
And during EVAs, a simple thing such as an unsecured tether or a misfiring emergency thruster can also spell disaster. Being outside of a spacecraft on a spacewalk is the most dangerous thing an astronaut in orbit can do. One false move can be deadly, especially if that false move takes you away from the spacecraft.
There was an instance on one of the Russian space stations, the Soyuz, where one of the crew members was not tethered, and he was in the airlock area watching the other crew member, and he slowly started to drift out, and the other cosmonaut saw him and grabbed him. An untethered person in space without appropriate propulsion system to get back would be very, very serious. I mean, basically, you're lost at sea.
Even with a propulsion system, it can fail or run out of its limited propellant supply before the astronaut reaches safety. The astronaut will simply keep floating off into space. The International Space Station is unable to chase someone down, and if the shuttle were docked, it would take too long to undock and mount a rescue. In this nightmare scenario, the astronaut will likely have several hours of oxygen remaining to contemplate the end.